Maurizio, who's somewhere in this room and much smartly dressed, much more smartly dressed than me, but you get me. Sorry. So we're presenting a possible infinite dimensional extension of categorical quantum mechanics using non-standard methods. So what's the main motivation for this work? Well, we really like diagrammatic methods from categorical quantum mechanics, but they tend not to work very well when you try to extend them to infinite dimensions, mostly because one fails to have dagger Frobenius algebras which are unital. And this might seem something which you can obviate to by considering H-star algebras, and that's true for the orthogonal basis characterization, but you still lack group algebras because they give unbounded operators. And as a consequence, you have no strong complementarity. You can't do Fourier sampling in any sensible way, at least not diagrammatically. But there's more, it's actually not dagger compact, so there is no nice diagram manipulation where only the topology matters, because you don't have cups and caps. You don't have traces, because they would give rise to infinities. And there is no operator state duality. Furthermore, there's a lot of other useful gadgets that are quite commonplace in quantum mechanics, like Dirac deltas and plane waves. They're just used as tools very often, but we still can't capture them in Hilb in the usual categorical formulation, and we would really like to do that. So we asked ourselves the question, can we use non-standard analysis to do something like this? And it turns out that, well, yes, we can. There's a lot of things that we can recover by using non-standard methods. So first of all, non-standard analysis is usually considered a way of using infinitesimals to derive some results in standard analysis just by doing multiplications and divisions and without taking limits. However, if one looks into it a bit more carefully, it's a model theoretic way of treating limit constructions without actually having to take topological limits. And in particular, well, natural numbers are unbounded, it's standard ones, so we have no standard infinite natural numbers. And if we take any sequence indexed by natural numbers, there's a unique extension to infinite indices as well, which is something we will use very heavily because we want to handle series without actually taking limits. So what we do is we consider the sequence of partial sums, which is defined for any finite natural. We extend it to infinite naturals, and then we say that our infinite sums are just that sequence evaluated as some infinite numbers. And that turns out to work fine. That is what non-standard analysis gives you. So that's a pretty nice trick, but in the real case, when you take sequences of reals, there are a lot of structural theorems that tell you that actually you're not buying a lot with this. Everything could be obtained by limits, essentially. But when you deal with infinite dimensional Hilbert spaces, that's not strictly true. In the sense that you get some genuinely new finite vectors which are not near standard. They're not infinitesimally close to some standard thing that you could have obtained otherwise. They're actually finitely far from any standard vector, and they're still finite. So you can still do some sensible physical operations on them, but they have new properties. That's an example. You just take an infinite orthonormal basis and you take an infinite sum, and then you renormalize that. That's definitely a norm 1 vector, and it's not infinitesimally close to any standard vector. Depending on what the basis is, that could be a Dirac delta, it could be a plane wave, or something else. And in the example I'll give in a little bit, it would be a Dirac delta. So we need to define a category, and to do so we take our objects to be pairs specified by some standard separable Hilbert space, some choice of orthonormal basis, and then we have to fix a dimension for our object. If our original space was finite dimensional, then the dimension will be the usual natural number, finite natural number denoting the dimension of the original standard vector space. If it's infinite dimensional, then we fix some infinite natural. And different infinite naturals will give different dimensions which are not exactly equivalent. But we'll see that that is consistent with the definition of dimension in dagger compact symmetric monoidal categories as the trace of the identity. I'll show it in a little bit. So our morphisms are just matrices where the matrices are not indexed by some natural numbers from 1 to some finite n. They're now indexed with natural numbers from 1 to some possibly infinite natural number. They're still well-defined matrices, and we can still sensibly write our morphisms like that. That's not just a symbolic manipulation or a trick, that's actually a sum. That's a well-defined thing in non-standard analysis. And our identity is a legitimate infinite sum of one-dimensional projectors, and we can do all the usual operations. So we can do matrix composition, we can do tensor, we can do adjoints, we can do matrix addition, and this becomes an enriched dagger symmetric monoidal category. with no standard complex numbers as the field of scalars, not the standard ones. So this will be our arena, if you wish, where we can try and do something more that we couldn't do before. And indeed, we get unital commutative dagger Frobenius algebras. You just take the usual way of writing them as sums of a ket and two bras, or a bra and two kets. But instead, you now take infinite sums, and these are well-defined objects, and they give you a legitimate unital Frobenius algebra. And as a consequence, the category is dagger compact. It has caps and caps, and it's a usual form, again, where now the sum is infinite, and the trace gives you the same infinite integer that we picked as the dimension. So this is all self-consistent. As a case study, we'll consider wave functions on a one-dimensional space with periodic boundary conditions. So we take L2 of R modulo some finite length lattice, or if you wish, L2 of S1. And we take the standard orthogonal basis of momentum eigenstates. Since the underlying space is compact, these are genuine standard vectors which we can manipulate and choose as an orthogonal basis, and we can normalize them. And we fix a dimension, and we fix it odd just because we want to write our sums like that, from minus omega to plus omega. It's just notational convenience. It had really nothing to do with anything. It's just pretty clear. And we get the classical structure that would correspond to the momentum observable, just like that. We just sum the momentum eigenstates, and we obtain a Frobenius algebra, which will give us the momentum observable. However, this doesn't really buy us much, in the sense that this first part, at least as a morphism, already existed as an H-star algebra. We can define, and we will define, the position observable, and that can't be defined usually because it would give rise to an unbounded operator. But in the non-standard setting, one can try and do that. So first, we try to define the position eigenstates. Those are Dirac deltas, and they're not standard vectors, so we have to use some different trick to define them, and we define them as appropriate infinite sums of the momentum eigenstates with phases. And then we prove that they behave, there you go, they behave exactly as you expect deltas to behave. They behave as evaluators at the points of your underlying space. So these do behave as Dirac deltas, and as an additional confirmation that they actually are the eigenstates that we're looking for, we can look at the action of momenta on them. So we take the monoid fragment of the momentum observable, and we expect that to act as the translation group in the underlying space, and that is indeed the case. That gives us the translation group back. So these are the position eigenstates we are looking for. And now the question becomes, how can we combine them into a position observable if they are a continuous family? Because we don't have integrals. Integrals don't exist, we only have sums. So the trick is, for the momentum observable, we first define the observable from the basis, and then we show that the monoid fragment acts as a group symmetry. And for the position observable, we will do the opposite. We will first construct the group algebra for boosts, so the translation in momentum space, and then we will show that that corresponds to a Frobenius algebra, which gives you the position observable, and that's exactly what we do. We first construct a multiplication which adds the momenta, and the unit is just the zero momentum eigenstate. And then we show that that's, in fact, a commutative dagger Frobenius algebra, and we show that that's strongly complementary to the momentum observable, i.e. it satisfies the Weil canonical commutation relations, which is what you would expect from the position observable. And indeed, it does copy exactly the rescaled position eigenstates, which is again what you would expect from the Frobenius algebra associated with the position observable. So in conclusion, we've done some things, we've shown some examples, but there's a lot of work that still has to be done, and that's really interesting and really exciting. We already started working on some of this, and we have already a draft of a more general definition which allows for non-standard basis. So we don't want to start from a standard basis and extend it, we want a legitimate non-standard one, because we might be able to do more things with this, and in fact, turns out we can. And we already started working on CPM and infinite dimensional quantum classical formalism, and we want to have a lot of other examples. So we want more examples with an abelian underlying translation group, we want examples with a non-abelian symmetry group, which is still compact, and that should still be treatable, even though one has to consider a non-commutative observable, in a certain sense. And, which is slightly harder, we want locally compact abelian symmetry groups, because the traditional case of momentum and position lives on R to the n, or R if you wish, and that's locally compact. And that's slightly harder, but it turns out it's still treatable. And perhaps most surprisingly, we can treat some non-separable spaces. And we can do some toy examples from quantum field theory. But that's it's a bit in the future. Not right now, but we already started and it seems quite promising. Okay. Well, I guess my time is up. Anyway, the next slide said thank you very much for your attention, and if you have any questions, I'll be happy to answer them.
So you still have a trace that satisfies the cyclic property and is linear, right?
Yeah.
So how do you do the locally compact, non-compact case then? Because if you do it for the reals, presumably you get a pair of operators P and Q such that PQ minus QP is equal to the identity, the usual form of the canonical permutation relations. The trace of the left-hand side has to be 0 by linearity and the cyclic property of the trace. And the trace of the right-hand side has to be the dimension, which in your case would be a non-standard number, non-standard natural. So how do you avoid that?
Because you're considering the position and momentum, the differential generators.
Yeah.
And here you never have the differential generators. You
So
only have the actual.
you can't get them out of the while form then?
No, the vial is already exponentiated.
Yeah. So what happens if you evaluate the vial form at an infinitesimal time?
That's an extremely good question, which I've not looked at.
Because
But
that
I
would
will be
normally be the infinitesimal generator.
Possibly, but I'll have to look into what happens when you do it in the non-standard case, because it might be slightly trickier. These are unbounded operators. So if you have infinitesimals, it doesn't get. So if you multiply an infinitesimal by an unbounded operator, there is no guarantee whatsoever that the thing you obtain will be an infinitesimal operator. It could be a finite operator. So your trace might not give you exactly the usual argument. And this might save you, but I will come back to you and I will tell you how it works out.
Okay.
There are several more questions.
Yes.
In contrast to that last question, which was an extremely good question, this is an extremely stupid question. Do you have any idea what happens to Gleason's theorem?
No, not yet. But yeah, that's a good point.
Yeah. There are several others. Yes, you were first.
Okay. So, just a quick question about the case of when you have a generally infinite dimension. How do you choose the, let's say, the extended natural number? Because in the standard case, all the separables with the space are all isomorphic. So, instead in your presentation, there's kind of grading on the dimension. So, how do you choose it?
You don't choose one. You have a category that has all the possible ones, and when it comes to bounded operators, they turn out to be all equivalent. When it comes to unbounded operators, they turn out to be, there's a suitable injection from smaller to higher dimensions, but if you try to compress, you might lose something. Now, for all bounded operators, that's something you lose is always an infinitesimal, and it always gets traced away when you go back to the standard category. For unbounded ones, you might get slightly inequivalent representations. But there's an entire family with an entire action, a translation action, so it doesn't really matter. You're taking unbounded ones anyway. It's an arbitrary choice.
Ross?
What do you expect CPM of star Hilb to be?
CPM of?
CPM of
Yeah.
your star Hilb, what do you expect it to be?
Especially in relation to von Neumann.
Yes. So since it's Dagger compact, you just construct CPM. Now the question becomes what exactly it looks like, and I would think it's a non-standard extension of the CP maps, but I will not bet anything on it right now. Especially since I'm on camera and then the folders can. If you want to do it privately later on when nobody else asks, I can bet something.
Yeah, we can turn the camera off. And,
Fair.
Chris, you had a...
So the objects have a sort of distinguished basis, and if you copy that, you get a Frobenius structure. Do you know anything about the converse?
Yes. So
They're all of
there
that
is.
form?
Yeah, we have a theorem in the actual paper that states that any basis gives you a weakly unital Frobenius algebra, so one which is unital up to some infinitesimal. So when you go back, it would be any result obtained applying a weakly unital one would still be strict, because you always do the going back to standard spaces up to infinitesimals, but in the category itself it's just weakly unital, but you still get Frobenius algebra.
Maybe
So it
to
is
connect-
unital, but up to, and if it is, so if you take the co-unit, for example, and co-multiplication, you get the identity up to some infinitesimal operator.
Maybe to connect to the last question, do you also know something about the non-commutative ones?
What do you mean? Whether you
What
can
are the
construct
non-commutative
non-commutative?
Frobenius structures in the category star Hilb?
Yeah, you can construct one for non-abelian groups exactly as you do with group algebra. So you can do group algebras in general, really. You pick a basis, you pick a group, any group on it, and then you construct the group algebra, and that you can always do.
Yes, Ross? Final.
So, two words you didn't say in your talk were transfer theorem.
Ha!
I was wondering if there's any hope to use infinite dimensional security in an outside model to learn something about, say, photon number states, or something really concrete.
So there is a equivalent. There's an equivalent to the transfer theorem, if we wish, a generalized version, which is part of the theorem where we prove that you can embed separable Hilbert spaces suitably into this category, which says that if you want to prove equality between two morphisms which are standard in separable Hilbert spaces, you can always lift them and prove equality in the higher category, and the equality will also hold in the original category. So that is a sort of a up and down transfer theorem. So the up transfer theorem is always pretty trivial in a certain sense, because you can always just embed the original standard boundary maps, and those are maps here as well. But then the question is, can you always pull it down? And the answer is yes, up to infinitesimals. But if your original morphisms were both standard, then the up to infinitesimal returns you the standard part. So that's always, you can always do this procedure where you want to prove some equality, but it might be very hard to do with standard methods without cups and caps and diagrammatic methods. So you lift them, you prove the equality with whatever you want, and then you are guaranteed that the equality will also hold in the original category, which is the sort of generalized version of the taking the standard part, if you wish.
Okay, are there many more questions? Well, one. Yes, please go.
I have done very similar thing very long ago, and I started with hyperfinite algebra group and making non-standard unitary representation, and then making standard part to obtain the usual Schrödinger representation. And also such kind of the algebra in a finite dimensional cutoff of the boson field, or is given by Burnett. This university before, and Pep in Australia. They calculate the number stage, cut off some very large number. But they don't consider the non-standardized, just the standard. But they have the many calculations about all the algebras, and that was following many papers published. So such kind of the commutative and program is discussed in many papers.
So the one that was mentioned before, the
Yeah.
commutator. Yeah, sure.
Because in that case, your translation come back from infinity plus infinity to minus infinity, or infinity to zero. Because your translation becomes just rotation, but actually space-time is not. Right? So that's different.
Actually, I have a very brief point on that. Very extremely brief. Yes, so there is a rotation going on here, because if you look carefully at that group algebra, that is a rotation. But it turns out, because of the way the non-standard numbers are done, the rotation is on the standard integers plus some other stuff, but restricted to the integers, it's just the usual translation. The integers never come back to themselves. It's just a weird, it's an issue with the topology of non-standard integers, but it is a rotation on the non-standard fragment, but on the standard fragment, it's the usual translation. So you never have the coming back.
Yeah.
Thank you very much. Very interesting work.